her expertise and efficiency and just, support that we have received. So we really, really appreciate that. I will just start in Serbian for about 2 minutes, just to greet the audience and to let them know what's going on, and then you can start your presentation. Is that okay? Thank you so much. Dakle, dobrodošli svi na ovu našu današnju konferenciju koja predstavlja završni događaj projekta Kvantna muzika i izvan kvantne muzike. Mi smo to započeli još 2015. godine i evo sada privodimo kraju. Trajalo je malo duže nego što je bilo prvobitno zamišljeno, zato što su se pandemijske okolnosti isprečile. Međutim, evo, uspeli smo sve da finiširamo. Tako da mi ćemo najprije imati jednu prezentaciju samog projekta. Olga će se nama obratiti u ime Evropske komisije. Reći šta je u stvari uloga programa Kreativna Evropa, na koji način oni podržavaju umetnike širom Evrope, koja su očekivanja, ciljevi i tako dalje. A nakon toga ja ću vam ukratko predstaviti naš projekat i onda od 12 sati imamo Klausovu prezentaciju. Tako da smo, da kažem, generalno dobro nam je prolazno vreme. Okay, so now I'm really happy to give the Zoom podium to our Olga Zismanidi, who will tell us more about the program Creative Europe, about the support that they provide to artists throughout Europe, the goals of the whole enterprise, and anything else that might be of relevance. So thank you so much for joining us today.
Thank you very much, Ivana, for having me and for giving me the floor to opening this special celebration for quantum music. I have not prepared anything detailed about the program, about the funds that we are providing, but I'm happy in case that we have any questions before that. I just want to say a couple of words about quantum music, which is not a stranger to the Creative Europe program. And before that, just to say, to put it in a broader context, if you allow me, the project, because
yes.
From rhythm laws and multi-list of symmetry, music these days, which is the priority of the Creative Europe, has been pushed over the limit. And indeed, quantum art can make our mind wandering in unknown journeys, full of unusual sounds and ideas, for new artistical creation, aesthetics, and application of quantum technology that may seem endless or can be structured upon maths and logic. I don't know, you are the experts, whether quantum randomness can be predicted when quantum art enables the experimentation of random potentials outside our standard cultural conditionalities and the traditional dimensions of music. But I trust that this experimentation can help us to innovate within virtual and physical performance spaces, to discover and to translate stellar information to digital art that can lead to breakthroughs and shape the future. During the last 7 years, the Beyond Quantum Music project showed the Creative Europe program's great blend of creativity with the generation of original compositions, new sounds, and other interactive works that can add, and I think this is very important, to new cultural and economic values to the European music and scientific heritage. Regardless now all the necessary balancing acts for instance, for them to secure the fundamental rights, there are limitless possibilities for new artistic shares by the human-machine interactions, for advancing the creative economy with a generation of new revenue streams, and for bringing together creators and citizens. And this is powerful. The EU and its funding programs, notably the Creative Europe, provides the funding framework for the creative ecosystem, which is called upon to be creative on the ground on its own right. Art, music, and science has a powerful renaissance to unlock the strategic development goals for industry transformation, innovation, infrastructure, and partnerships. Now, the new generation of art and quantum music can inspire citizens to think life in new ways and potentially contribute to other strategic development goals for quality education and sustainability. I think I would like to stop here and to follow up your knowledgeable and expert exchanges on the project, to listen your experiences, what were the problems, what were the advantages, and to look deeper into the unknown but very much promising field of quantum music and digital arts. So thank you very much for coming in. And of course, if you would like to explore more the Creative Europe program, I'm very happy to do that with you tomorrow. But yeah, just to give you some time. Thank you very much.
Thank you so much, Alba, for joining us. I don't know if you can hear the applause. I hope you have. Well, I would just like to continue now. So I will now present the project, provide a very short history of the 7 years of quantum music, how we started and where we are now, because this is really sort of a lifelong project now for us all. But at least we can now sort of draw the line and see how we got here and what needs to be done next. I will try to illustrate my presentation with some of the recent recordings, because we had this tour in September and October, where the Beyond Quantum Music program was performed in 4 cities, and also we had an exhibition, so we made some recordings from all these events. They're still not being edited, so these are kind of raw versions, but they're all very illustrative anyway, and they will show you what sort of directions we went to. And afterwards, at 12 o'clock, we will have our wonderful guest, quantum physicist Klaus Möller, who has been of a really great help since the first project. So we got to know him thanks to Kim Helveg, the composer from Denmark, who used to be one of our collaborators and partners on the first quantum project. And Klaus was also very forthcoming in the sense that obviously the pandemic caused many problems in terms of logistics. Universities were closed, the laboratories were closed, all the teaching had to be done online, and this put a strain on the activities which were related to the research plan for this project. However, we found a solution when Andrija Pavlovic, one half of the LP duo, who is also here with us, so he won an artistic residency at the Technological University in Delft, in the Netherlands. And they also have fantastic, several laboratories actually, where they also do quantum, nanoscience, bio-nanoscience, so all these most advanced fields of science, and they're all enthusiastic about music. So he found the perfect place to actually do the research part of the project. Then he brought Sonja, the second half of the LP duo, to be there in Delft with them, and then Klaus joined them at some point. Klaus is also related to Delft by virtue of having some of his former PhD students and postdocs who now have their own labs in Delft. So it's really a well-connected network of people doing cutting-edge research, and we were really, really honored to just be able to peek into their fascinating world and see how we can contribute to it. I'll just take some of my notes so that I don't blab too much. Just take where you are. Because I met kind of a concept. Yeah. Okay. So, first I will give you a very short breakdown of the quantum music project, how it first started and how we actually all got to know each other and to work together. So the two people who actually originated the project were two Belgrade guys. One of them is Vlatko Vedral, who is now a professor of quantum physics at the University of Oxford, formerly a student of the Mathematic High School here in Belgrade. So he is one of the most renowned European scientists of this era, and he has also been very much engaged in popularizing quantum physics and all the related phenomena across many platforms. Because for most people, when you say something like quantum physics, quantum particles, that invisible world that we are actually a part of, but we do not understand it, for most people it is really hard to comprehend. And that's why many scientists, including Klaus and his collaborators, have actually done a lot to try to bring this world closer to us so that we can grasp what it is all about and how we all actually consist of energy. What looks like solid matter, what looks like a firm state of being, it is actually all energy. And very different forms of energy exist, and they study it all, and they try to explain it to us mere mortals. And then the second guy was Dragan Nokovic, who used to be Vlatko's high school friend here in Belgrade, and they used to play guitars together. They were enthusiastic about music. So Dragan then graduated from the Faculty of Electrical Engineering and then did his PhD in acoustics. And he's now one of the foremost experts in the Balkans about acoustics of spaces, especially the closed spaces, venues, but also churches, concert halls, anything really. And so the two of them met up after a long time, played guitars together and said, let's do a project together. But they didn't know where to start. They just knew that they wanted to do something related to physics and music. And so they started to assemble the team. That was back in 2014. So first they drafted Sonia and Andrea because they're superstars and everybody knows them and they've got their own audiences and following. And they're keen to explore new repertoires. That's a very hard thing to find when you have good performers. Lots of them are very happy to just be performers and to play standard repertoires, maybe some contemporary music, but they are not really into experimenting that much. Whereas Sonia and Andrea, from the beginning of their careers, first separately and then as a duo since 2004, they have always wanted to do something new. So they established this piano duo, which is also a rock band and an electronic music band and like a performance act, all in one. And they were their own managers, and they just had this idea, we don't want to be bored. We want to do something that will keep us motivated, and by doing something interesting, we will keep everyone else interested as well. So they started to diversify into playing in bands, composing their own music, first as for the bands, then as applied music for theater, for film. Then they started releasing their own music, and now they have quite a diverse discography consisting both of the music by other composers and their own music. So they have, for instance, they recorded the whole works for two pianos by Kim Helvig, who I have already mentioned. And then they invited me. At that point, I had only just returned from United Kingdom, where I lived for 7 years and where I completed my PhD. And they were like, yes, we need someone who will be the mastermind of these songs, and someone to do the boring stuff. Oh. And I signed up to do the boring stuff just because I wanted to be involved with something interesting. As a musicologist, I have felt for a very long time that contemporary music has become very stale and predictable. Not much interesting was going on. And, I wrote a book about Karl-Heinz Stockhausen, one of these big mavericks of the 20th century avant-garde. And I was like, if Stockhausen and his cohort could do these interesting things 70 years ago, why can't we do it now? Let's get on with it. I don't want to be writing about someone else's work anymore. I want to be involved into actually making something new. And so I signed up for this, and then we started gathering together international consortium of partners, and that's how we started the first project in 2015, and we were very, very lucky to win the support, the grant from Creative Europe. It was the first time that an institution from Serbia, the Institute of Musicology of the Serbian Academy of Sciences and Arts, could actually become the project leader. Serbia, as you know, unfortunately is still not a member of the EU, but at least we have access to all of these different programs offered by Creative Europe and other funding bodies within the European Commission. But obviously people here did not have the expertise, they did not have the support from the local ministries, so we all had to kind of learn as we go. But we were brave enough to just jump into the unknown and see what we can come up with. So the first project lasted for approximately 3 years. It was done before the pandemic. Everything went more or less as planned, and we even managed to do much more than we initially intended to. So, for example, Sonia and Andrea managed to even perform the program in Singapore. They received an invitation to go there, and they also found a fantastic quantum lab existing in Singapore and established some contacts there. Then we created this whole network of scientists working on different aspects of the quantum world and trying to interact with music. The thing is, once you start doing artistic research, we had to understand, yes, we cannot become quantum scientists. That's not the goal that we wanted to accomplish now. But we wanted to understand the quantum world, and we wanted to see how we can use it to draw inspiration for artistic works. And there are many, many, many different ways how this can be done. Some of those we explored. I'll just show quickly for those who are watching online. So we had the first conference on quantum music here in Belgrade in 2018, and we published this issue of the journal Musicology with texts mostly in English, where we sort of got together a team of kindred spirits, people whom some of them we hadn't known before, but they were all happy to share with us how they approach quantum music. And so we had someone like, for example, Alexis Kirk, who is originally a mathematician and who actually programs quantum computers. He does not have sort of musical training, so the results of his programming, the music that he generates is mostly random, aleatoric, but very, very interesting, and of course it changes together with the technology, which also changes all the time. Then we have Andrew Garner. He was one of Vlatko's former PhD students who ended up doing research in Singapore, in Vienna, in many different places, and who was interested in creating this device called the musical Mach-Zehnder interferometer. Then we had Klaus, who wrote about the quantum vibes of atoms and ichthyosaurus, one of these prehistoric, not prehistoric, but the extinct species, natural species. Then we had Kim Helvig, who wrote about his approach to composition, because when we first drafted him to collaborate with us, he was in a state of panic, because by that time he had been known in Denmark as a composer of not very serious music. He was doing some postmodern stuff, a bit of jazz, a bit of improv, a bit of anything, and Latin music, whatever. But then we were like, come on, Kim, you need to challenge yourself, you need to do something related to the art and science. And he was like, I can't do it alone, I need to recruit a friend. And that's how he brought in Klaus. And so they managed to collaborate on the first quantum piece, Superposition, that Kim wrote for LP Duo. And actually, what was really new about that piece, it wasn't, Kim could not really change his compositional methodology at that time, but he at least tried to imitate by his music some of the quantum phenomena. And in different movements of the piece, he actually showed how he interprets the phenomena such as superposition, such as collapse, interference, whatever, all these notions from quantum mechanics. And I will not repeat it all because it is all published and it is all available online, free of charge, in the repository of the Serbian Academy of Sciences and Arts. So whoever wants to read, feel free to help yourself and study all these fascinating articles. So when we finished that project, obviously we wanted to continue. So we applied for a second grant for the Creative Europe funding. But we actually wanted to expand, to go beyond the initial concept of the project by means of including artists from different disciplines as well. So we wanted it not just to be the LP duo and those of us who hang out with them, but actually to get to know even more enthusiasts who would be interested in joining in. And also we wanted them to use some of the sounds that we synthesized during the first quantum music project. Namely, we were able to create some new sounds based on the equations provided by Klaus, and we created a bank of sounds, and we made it free access and told people, help yourselves, do with this whatever you want to do, and try to come up with some interesting works. And then we, when we got the funding for the second project, it was with a slightly different consortium. Initially, we had LP2 and their company, the Institute of Musicology again as the project leader. We had Ars Electronica, a huge and very important electronic music festival from Linz, Austria. And we had a festival from the Netherlands, Today's Art. And also a school from Hanover, some of you have been there, the School of Music, Theatre and Performing Arts in Hanover. And they were meant to be an associate partner. We thought we can do no wrong. This is all super well planned, we know each other, we're all friends, this is all going to be very easy. However, then the pandemic happened, and all of a sudden all the good plans went down the drain and nothing could be done the way we wanted to, and then we had to change our plans as we went along. So we were like, okay, let's do first the technical part of the project, which was the development of the new hybrid instrument, the keyboard instrument that would now perform many different things. I will play you some examples later. So this originated from the idea that we had during the first project to use some sensors to attach them to a normal key piano, grand piano or upright piano, and to then transform it into an electronic instrument, which can play live, combining the sounds of the actual piano and the electronic sounds. We designed the software interface to be able to do this in real time and to manipulate the sounds. But the first technology, we weren't so happy about it because it consisted of magnet sensors, and it was a bit difficult to install and difficult to adapt to different types of piano because every piano is different. So we were like, we need a different design. And then the idea was to use the optic technology, optic fibers, and then to implement those for this second prototype of the hybrid instrument. So we found a great team of HTEC, an American company which has its offices here in Belgrade, and they were able to help us develop the instrument that we wanted to. We obtained a huge grant from the Serbian Innovation Fund, Fond za inovacijnu delatnost, Republike Serbia, and that's how we managed to finance this development, because every development of a new technology is tricky because you never know if you're going to be successful. So a lot of things need to be planned in advance, and prototypes need to be tested, and then components change, blah blah, until we reach the final product. So that part was done successfully, and it could be done during the pandemic because each part of the team was working in their own sort of office, and we communicated on Zoom all the time. I was writing reports, everybody else was doing something useful. And then the second part was actually to start composing music. So this is when Sonia and Andrea started to do their own work, and we also opened a call for artists worldwide who, not just composers, but also visual artists, performance artists, multimedia artists, whatever, to send us their works inspired by quantum world. And we were really surprised to receive 120 applications. We did not expect so many enthusiastic replies. Some of the applications weren't so good, so we discarded them, but lots of them ended up being quite interesting. And so we made this short list, which wasn't really short. It consisted of about 20 pieces, and we wanted to see whether we will be able to stage them and to have a tour going through these 4 cities. But then the pandemic went on, as you remember, throughout the year 2020 and 2021, and we realized that the tour that was supposed to happen in the autumn of 2021 had to be postponed. Because it had to be done in the autumn, because that's when the festivals, Ars Electronica and Today's Art, take place, and those were their annual editions. But both in 2020 and 2021, they had to do their activities in a very sort of reduced way. They didn't have many live audiences, everybody had to wear masks, nothing could be interactive. It really made everyone's life very complicated. And so we decided to postpone the tour until 2022, hoping that things would work out better. In a way they did, because finally the restrictions were lifted sometime during the summer of 2022, but then another problem emerged, as Olga remembers all too well. We had a problem with this partner from the Netherlands, Today's Art, because obviously they ran into financial troubles, but they didn't bother to tell us. Actually, we had to beg them to let us know what is going on, because we were repeatedly asking them, why aren't you doing your part of the work? What is going on? Will you be able to complete any activities? They kept us in the dark for many months, and finally Olaf, the leader of that, confessed that actually they can't do it. Then he wanted someone else to step in instead of him, but that didn't work out either. And so Olga advised us that the only way to ensure the completion of the project would be to find a new partner, which wasn't so easy, because this was happening in the summer and the tour was already supposed to start in September and October. So we had to kick out Today's Art, find a new partner, bring them in, convince them to join in, at a very late stage of the project, and just hope for the best. Luckily, Sonia and Andrea, being the superstars that they are, they have lots of friends, so they managed to find some partners from Croatia, from Split, which is a very interesting institute, medical institute for life sciences. So they do interdisciplinary research in many sciences, but they also have this art program and art residences, and so they were like the perfect fit for our consortium, and they were actually happy to join in. So we managed to do all the very complicated paperwork thanks to Olga's expertise and assistance. It was all done on time, and we managed to organize the tour. It had to be reduced in a certain way. Some things had to be adapted. The German associate partner also dropped out at some point because they had a huge backlog of the activities that did not happen the previous 2 years. They had to catch up with everything. So it all kind of worked a bit differently than planned. But in the end, we managed to have 4 concerts and to draw lots of audiences and to make good recordings, which will be later on produced and distributed, so we will have this kind of lasting trace of our work. Just to finish quickly, so we also had an exhibition here in Belgrade, a multimedia exhibition where we drafted some of these enthusiasts. Unfortunately, that short list had to be shortened again because everything became really expensive in the meantime, especially the flight tickets, visa situation became complicated. One of the artists, Arash Akbari from Iran, that was supposed to go to Ars Electronica, in the end he didn't go because he did not obtain the visa. So again, he had to sign up online. So these were all kind of external things that we could not influence, but at least we managed to invite some interesting people and to showcase this interesting program. So I will now just quickly read a few explanations by Sonia and Andrea, and then you will hear a lot more about the research that they did, both with Klaus and with these other scientists from Delft. But this is just to give you an idea how they approached these quantum phenomena. And again, this is just one of the options how these things can be done. So for example, May Day, we will hear that shortly. Here we dealt with the question of reality in a philosophical way. What is reality? Does it exist? Does it exist only if we observe it? The father of quantum physics, the Danish Nobel Prize winner Niels Bohr, formulated this in the following way, quote, "Everything we call real is made of things that cannot be regarded as real," end quote. Then we have the scanning tunneling microscope, and they say, we worked on the scanning tunneling microscope experiment with the wonderful scientist Sander Otte, whom we will hear tomorrow, who works in the quantum laboratory at the Technical University of Delft. In his laboratory, we directly recorded the sound of moving atoms. We moved them with a type of needle that actually looks for atoms. When the atom jumps, when the needle finds it, a change in sound occurs. Together with Sander, a great lover of jazz and piano, we assigned several harmonies to this experiment and built the composition from that material. The basis for the harmonies also came from working with him. So the path led us from recording and manipulating the sounds of atoms in the experiment to the harmonies that Sonia creates on the synthesizer and Andrea on the piano. Then they explain how they created rogue waves with another collaborator from Delft, Kobus Klupers. I hope I'm pronouncing that correctly. Then silence. This is also something worth reading very quickly. So they say the most poetic composition, silence, is related to the whole concept of quantum music and the idea that silence is actually identical to quantum vacuum. We started it by recording a deaf room in Delft for several hours. Then turned up the volume and were surprised at what could actually be heard there. Then we followed up on that silence with the idea of creating a composition out of nothing. Silence is my quantum vacuum. 0 point energy. Music energy. Silence is my music. These are just some of the poetic words that Amy, our artificial intelligence friend, interprets. Those of you who were at the concert, you heard Amy and Brian, these AI voices who actually read this poetry written by Sonia and Andrea. And finally, just a few words about qubit funk. We will also hear that one. We worked on this composition together with two wonderful scientists, quantum physicist Eliška Greplova and bionano-scientist Dimfna Meyer. They started working together and studying quantum systems, finding connections with neural systems, cells, molecules, and vice versa. Using quantum computers, the two tried to calculate and predict certain behaviors of neurons. Eliška and Dimfna extracted the frequencies of those qubit neuron experiments for us, which we then transformed into sound. First of all, we made a powerful bass line, on which we further added new elements, a minimalist accompaniment which transitions into the funk groove of qubit. Qubit is 0 and 1 at the same time, while bit is either 0 or 1. As you can see, so this is really a free creative interpretation of these quantum phenomena. If we tried to just reproduce this sound of the quantum computer or the sound of quantum lab or what we captured from atoms, that would be boring. And it's not the point of a creative projects such as Beyond Quantum Music, but we actually used those elements, they incorporated them in the music that they wrote, and then the visuals of the concert also were explanatory in a way of what is going on, and the written text as well, so we kind of created an immersive multimedia experience for everyone. Let's now hear a few examples from this. I will try to share the screen. Let me see if I can play it first. Stefan, when did you record that whole clip from Udapun?
Link that you sent us from Google Drive.
Yes, but there was another one from Sonia's Google Drive. I have it
Do you have
somewhere.
USB maybe?
Yes, I just might need to. Will you give me just a few minutes? In the meantime, I can play you some of the extracts from this multimedia exhibition that was the final event of the tour, where we invited some of these artists from all over the world to share their inspiration with quantum music with us. So we had Jerzy Suchanek from Czech Republic, Joe Biggles from United Kingdom, Tadej Drolic from Slovenia, who else was there? Timo Holland from the Netherlands. There was an installation by Dragan Nokovic, whom I mentioned in the beginning. Andrij Andrić, a very interesting guy who is originally Serbian but lives in Denmark now, and we made them play their music for us or show their installations. This one is not compatible. Just let me see which software is compatible with this format. Open this.
Windows Media Player.
Windows Media Player. Recommended. Oh, I hate Windows computers.
No, those
Maybe you can.
Media Player.
films and TV.
Not now. Not now. Not ever. Not now or ever.
Sorry, change of plan. Now, let's just go. Can you open your email here?
Yes.
Just to find that link, and we will play it directly from Sonia's Google Drive.
And also we can play this YouTube link if it's. I
No,
can
but I
send.
wanted to play the qubit file
Yeah.
Mayday.
Cool.
Because if I try to sign up to my messenger, then it will ask me again for passcodes. Whatever. That one, yes. And just share the screen.
Koji ćemo deo?
Pa idemo, evo.
Aha,
Da li je multiple.
To. Main je da to. Taj main je tu.
Okay. I placed the one, two. have the visuals, we just need the sound. Is it muted here also? Okay, I'm screen sharing, but where is the sound?
It's good.
Yeah. No, we need
Ovdje
to.
kaže da čuješ.
Can you hear it, Olga?
Ne čujemo mi ovdje.
Maybe you put
Yeah, we here cannot hear it, and I will have to.
I can hear it.
Okay, you can hear music. Okay, let me just show you the qubit. So those who are listening online will be able to hear. Let's first hear Mayday. Now we can just see the picture, but we can't hear them.
Silent movie.
Yeah, I will have to replay again.
voice on computers.
Jeste,
Mhm.
ali zvuk ide učesnicima
Ide
Zooma.
tamo, za Zoom.
Aha, I have the sound here.
Okay.
Maybe you can play the sound.
Yeah, but that's not important to me.
Yeah. Now Klaus is live broadcasting for us here.
Da, da, da.
There you can see the setup. So they have both these hybrid devices on the pianos and the synthesizers and the computers which have the software to actually control what's going on. So yeah, quite difficult.
Možda samo ovo da pustiš qubit sa
Mhm.
laserima. Jer
Je.
su tamo laseri ili...
Da, i na kraju
Aha, to je to.
Now you can see she's playing on the piano. My AI voice.
Artificial intelligence. Now we know who is behind.
So you hear the sound of the quantum computer. I'm very sorry to stop them. Now let's go back. Može samo da mi vratiš.
But everything will be online on the
Yes.
quantummusic.org, so there will be more time.
Yeah, sorry to interrupt them. We will play this during the lunch break later. But I think it is, we will prepare all the recordings, both from the exhibitions and from all the concerts. They will be available online when we start to prepare this final report. So I would like to finish my presentation now, just to set up everything for Klaus. Again, I really want to thank Creative Europe for giving us the funds and the platform and the connections to be able to actually do something like this, to create new instruments, to create new music genre, to connect art and science in ways that maybe they haven't been connected before, to engage more people from outside of our narrow circle to also become interested in these sorts of phenomena. And now we hope that this is going to emerge into a whole new tendency in contemporary music. We have now applied for a patent for these instruments that's been made, but it takes a few years to be approved, so it will not be commercially available soon, but we have the prototypes, and in due time this will also be sort of a major technological innovation that we have created also as a part of this project. So thank you for listening to this. Thank you so much, Olga, for joining us now, and we will just quickly set up everything for Klaus, and then he will take us on a journey to this unknown world. Thank you so much.
Well, thank you very much. Before I start talking, I'd like to thank Ivana and my wonderful colleagues here in Belgrade for the invitation to come back. We have all had years with COVID, as Ivana was just telling. It has affected physicists, scientists, the whole populations, of course. And we are still not completely used to being back on the train and giving real talks. I'm happy to stand here in front of my screen. I was kindly asked to sit down and talk into my computer a while ago, but I've been doing that the last 2 years. I don't want to talk into a computer anymore in my life. So anyway, I am very honored to be allowed to give a talk here at the concluding seminar of this network. I was not part of the quantum music project when it started, but I became part of the project very, very early. And it has been a fantastic pleasure for me. It has been a great pleasure to get new friends from outside the sciences, and we have had a long and still ongoing collaboration with Kim Helvig in Denmark, who really brought me to this project. So the title of this presentation, I call it Science and Music Where Curiosities Meet. I'm at the Lisbo Institute at the University of Copenhagen in Denmark. And so now we just have to make sure that this works. Okay, there's always something that goes wrong with this presentation. Okay, I'm sorry about that. Now it's my talk, yeah, okay. So a brief presentation of myself. I'm a physics professor, as I just said. I'm researching quantum physics and quantum technologies. I'm actually working on quantum computers. I have my name attached to one of the best quantum gates applied in quantum computers. I'm also doing a lot of teaching and outreach. I've given more than 200 popular lectures on quantum physics for broader audiences. I've written many articles, and I've also written a book in Danish about quantum mechanics, a popular book on quantum mechanics. I do play the clarinet and saxophone and piano myself, but you don't want to hear it because it's very amateurish, and it's only for fun. It's nice to do things for fun. I actually also do physics for fun, but I also get paid to do physics, and I also do that part of physics. So, very curiosities meet. So, I just looked up Webster. Curiosity, plural form is curiosities. So one meaning of the word curiosity is a desire to know. So your inquisitive interest in others' concerns, or an interest leading to an inquiry or intellectual curiosity. There's also an archaic form that means undue nicety or fastidiousness. And then there's a third form, that one that arouses interest, especially for uncommon or exotic characteristics. So she's a real curiosity. Or as an unusual knick-knack, as it's called here, the antique shop was full of curiosities. So the odd things. And of course the curiosity I'm talking about is the interest leading to inquiry, which is really what drives both me as a scientist, but also of course a creative artist of any sort. Also the uncommon activity, because quantum mechanics is uncommon, and I think that many spectators and many users of art are of course also seeing the art first being uncommon, because you present things in a new way, sometimes in an abstract way, sometimes you also leave the piece of art without being absolutely sure you understood what you have been just witnessing. And maybe also the knick-knack part is also part of it, because there are real knick-knacks in quantum physics. Great word, knick-knack, I had been thinking about that for years. So what is it like to discuss physical music with composers and musicians, and what can we learn in that process? So since I told you I just do all these significant outreach activities, many of them were attended by artists over the years, and they actually came and presented themselves to me and said, you know, I'm a painter, and I'm coming to this thing because I'd like to see if I can get some inspiration, or I'm a writer, or I'm a musician, and it has been very, very exciting. They brought up questions of a completely different and very competent nature than the more general public questions. I actually still remember the first lecture I gave here in Belgrade, I think it was in 2017 or 18. 18, yes, where there was a talk, and of course this was the music conservatory type audience, and I was completely stunned by all these fantastic questions, because they were all creative, and they all were spurred by a deep knowledge and deep training and deep comprehension of complicated material that was now being put in context with what I was talking about. And it was really very clear to me that this is a direction that's worth pursuing. Not only because it's fun or exciting or interesting, but also because it brings people together with lots and lots of experience and knowledge and creativity. And it becomes a dynamite activity. It's very exciting. So of course I'm using all my dirty tricks from communicating to kids and to normal public to also try to sell the message of quantum mechanics, but also try to make it understandable from different directions. So I'm using always lots of metaphors, lots of analogies, and of course when I'm talking to a person from music, I'm using metaphors and analogies that I think appeal to the musician. If I'm talking to a choreographer wanting to make a ballet, then I'm talking about motion, and of course I'm not trying to convince them that you should make the music look like my analogy of music, or you should make a ballet that follows my choreography, because I'm not the choreographer and I'm not the composer or musician, but it's just to establish the language. It's very precisely, as Ivana said before, of course you don't want to make a music which is a copy of what the physicists are doing. You don't want to do anything in art that's a copy of what we're doing. That's going to be boring. But maybe you want us to explain our stories with a vocabulary that is understandable, and then of course you are the composers, you are the choreographers. Again, one of the good questions from the Belgrade lecture was, how can you be sure it sounds good? And then Kim Helmi was in the audience and said, that's not my problem, that's his problem. Then I looked to Kim, and then, because that's exactly his problem, right? I mean, he's the one who can do that. So we're doing this visualization, analysis, a lot of listening to each other to find out what's a good way to communicate, and then we get going on this project here. So, and then what has happened, of course, with some artists, not only in music, but also other projects I was engaged in, we have been able to define common projects together, and then, of course, it's the projects that speak for themselves. I should say, though, that we have had a number of activities, also with Sonia and Antonia and others, where we make a mixed performance in the end. So you can put me on stage, and then for 12-15 minutes, I can talk about something. I can talk a little bit about the process, but also a little bit about the physics and what was the inspirational material for the performance that came. And we actually also, in Copenhagen, made a ballet with the Royal Ballet, and I proposed to the ballet choreographers and the director that maybe we should allow people to ask questions afterwards. And they said, that's very unusual. I mean, normally you don't ask questions after a ballet. Sometimes you may want to ask questions after a ballet. So anyway, we did it, and we had questions for nearly 1.5 hours. There was like 500-600 people audience, and they were asking questions to me, to the composer, to the choreographer. It was very democratic. It was very exciting. So maybe that's also a thing in the music world, to have a question and answer session after a concert. So, and then at the end of this presentation today, I'd also like to come back and reflect a little bit on what is in it for the physicist. What do I learn and where do I benefit, apart from having a super fun time and getting good friends? I mean, is there something I can bring back to sciences? And that is a hope that I also have with this work. So just one word or just one slide about outreach, because it's a little bit insane in that it's actually a very long tradition So these are old school buildings you find all over the country, started back in the mid-19th century from the vision that education should never stop in your life. And people living in the countryside typically had only a few years in school, and they decided all over the country that the people working in farms and wherever could go every week and learn a language, or learn about history, or learn something, right? And they still exist. Okay. In modern times, everybody has access to education or life. So now there are more recreational things that are going on in these schools, but they are still all over the country. And I think they are the beginning of a long tradition for telling things, because they would often invite people to come experts. So in fact, people like me would also 150 years ago travel the country to tell people in the countryside about science and whatnot. Okay, so now it's exploded, and at the Aarhus University, where I was until this summer, we have every day, 6 days per week, between 5 and 10 lectures every day that you can go, and they're public lectures in all of sciences. So it means it's a party every day at the university, because it's in the evening, people go home at 5 to 6, and then between 6 and 7, hundreds of people are coming. They have more than 200,000 seats booked every year for these talks. And we have a massive lecture series where we have an auditorium, and you may be impressed by the people in the room. There's about 900 people in this room, but in fact, this talk is being live streamed at the same time. And I gave such a talk in October. It was live streamed to 300 movie theaters in Denmark. So we had probably an audience of 40,000 people to that talk. Here I'm zooming, this is the Faroe Islands and Greenland, where they also get the talks. This is just a zoom in on this upper region of Denmark. It's close to the sea. These are fishing boats. This is especially the tradition of pulling the fishing boat on the beach every day. Very interesting technique. I'm showing you that picture because in that little village there are 84 people living, and 65 people came to hear my talk about quantum computers. It's not because Danish fishing industry is going to use quantum computers. This is because this is a thing that brings small communities together for a joint dinner, coffee in the break, and a beer afterwards. And the next 2 weeks they can all walk around in the streets and agree how stupid was that guy at the university. So I think we're actually fulfilling a number of missions. And I think Ivana was also commenting actually on the general public and how we are bringing people together, namely the people who get our stories. So actually, even without the arts, we as scientists have already cultivated that audience for a long time. And we are very happy to do that also. I think it serves so many good purposes. These are talks you cannot see from your home, because we found out we want to bring people together. Right? So we want them to come to a place where they discuss a little bit with the guy sitting next to them, because what really makes them happy about the experience is not how to build a quantum computer, but it's being with other people, always. So anyway, so this is warmed up, and so then on top of all these many popular talks, which are of course a little bit the same talk adapted to different audiences and all non-professionals, I got gradually invited to more and more funny special events. So there was a conference for theater directors, there was a quantum music thing at the Royal Theatre in Copenhagen, there were concerts, there was the library in Aarhus running the conferences. This is a conference with a famous Danish poet, Laugesen, and of course we were also at today's art festival with Sonny and Anthony. And it just became more and more. I mean, so we had all these things, and then with Kim, of course, Ivana did not show, but I mean, the collaboration with Kim was really fantastic. So we cannot do quantum mechanics on stage, but I can tell a quantum story, and then we can pick ingredients from quantum mechanics that can become the inspirational material. And I'll tell you a little bit more about it, but we took from the atomic physics textbooks, we took particular frequencies of light, and then we transformed those into the acoustic frequencies that you can hear, and then we turned it into sheet music. And these frequencies do not exactly match, but then Kim is not restricted to only the tones that are on the piano. He can compose with anything, because eventually we had to bring it back, or we chose to bring it back to being playable on a real piano, by rounding off to the nearest key on your piano, if you like. So it has been a fantastic collaboration with Kim, and also the concerts have been great experiences for me. So of course you know these famous
the Opera House in Copenhagen.
That's the Opera House in Copenhagen. And these events that's actually also funny, because we did a concert with the Aarhus Sinfonietta and solo cello, some other composition by Kim. And they said normally we outnumber the audience. So there would be like 28, 35 people in that example, and then there would be 15 people in the room, because contemporary music is sometimes hard to actually attract many people to. And I said, well, I'm disappointed if I don't have 300 people in the room when I give a talk. And so, and the combination was fantastic. So we actually filled up the house, and the opera told us they never had that many people for this type of event before. And because, so the Sunday night event in the beautiful foyer area in the opera, so I just talked to the building caretaker afterwards and said this was great. This was the final event of that year, and they were just super happy about it. So anyway, there are other symbiotic effects we can also do. And this is finally the ballet thing. Oh, sorry for the Zoom. So we have something from the ballet. I'll come back to a few of these things now in the next slide. So the communication that I'm trying to talk about here is that there's this. In my view, I like to see my artist colleagues as researcher colleagues as myself, because I'm investigating things and you're also investigating things, and so therefore the communication is actually like a communication between researchers. I mean, what is the problem? What is on the agenda? What is we like to get at the end? That's not such a different process, I think, in the sciences and the arts. So what we're talking about here is, of course, then the phenomena that we're bringing to the market, and the results and methods, the way we think, and the way we communicate and illustrate our science. That's really what I focus the most on when I've been together with our colleagues here. And so what I'll do now in the rest of this talk is that I will make an attempt to do two things at the same time. I would like to tell you about the process and outcome of this mixing of science and arts. So a little bit of a review, same style as what Ivana just did, but now coming down to some case studies. And then, while telling you that, I will also try to show you how I try to communicate complex theoretical material like quantum physics. So in some sense, I will also give you two talks at the price of one, because I also give you a little popular lecture on quantum mechanics. Right? So for those of you who have not already been exposed to the quantum stuff, there will also be an introduction to quantum physics in this talk. So you can see that both as your own little benefit, now you learn what is quantum mechanics, but you can also see it as the way I actually try to tell that story to professionals like you, and how I would do that and adapt it, of course, if I were to talk to somebody else. I think this whole project for me has been a good, a good introduction to how you communicate between two distinct professional communities, and maybe there could even be somebody who we could interest in looking more into that and extracting also something from that learning process. So now I'll do a little bit of physics on a few slides, but of course, given that you like music, I will motivate everything that we ever did in physics as being with only one goal, that is to do music. And it's not wrong to say that many physicists and famous ones have been deeply interested in music, and they have been working on music and the science of instruments, the science of sound. So just take Pythagoras, who is of course famous for his triangle formula that we learned in math, and some of you forgot again. Maybe intentionally tried to forget as quickly as possible. Pythagoras was also studying the theory of sound. So this is a rendering of how he's standing with string instruments, and he was actually finding out that if you have a string and you play it, and you half the string, you block it halfway, you get twice the tone, you get the octave. Sounds good, and Pythagoras was making a theory for that. Pythagoras also studied actually the motion of planets, and he had this funny idea that the motion of planets also occurs at very particular frequencies, like frequencies of sound, and there was something later called the music of the spheres, that there was maybe a divine principle in the creation of the world that was attending to music. So the same way as you can half and take the third of a string and you get nice harmonies, you will also have half and the third of periods of the planets orbiting the sun. It's actually accidental. There's no rule in physics who says that planets should do something like that, but there's going to be such a rule in quantum physics, and that's very exciting. Another great scientist, Ptolemaios, the greatest astronomer maybe of all times, lived in Alexandria 2,000 years ago. He made star catalogs, and he is famous for his star catalogs. He catalogued 5,000 or 10,000 stars, and his observations were actually the best in the world until around year 1600. So it's an amazing scientist. he was deeply interested in music, and he actually developed, of course, theory for the scale of music. And so and I think it was just completely natural for these. These were natural philosophers, but they were also deeply interested in any phenomenon. And music is a phenomenon much closer to our heart than the stars are, so that he would have to bring these things together. So there's a classical understanding and theories about sounds and music already back in the antique period. Now, the reason instruments actually make the sounds, the reason Pythagoras could identify the signal, the strings, is due to physical laws, and the physical laws actually came much later. Classical mechanics, and it's really surprising that it took so long. The laws of motion only appeared with Isaac Newton in the end of the 17th century. They were not discovered before. And there's one formula that says that the force is equal to mass times acceleration. Such a simple formula was discovered by that man. And it's the one who says that if you know what are the forces, you also know what's the motion going to be. And that's true if you throw a stone. That's gravity, which was famous. Newton is famous for the apple falling to the ground and for planets moving around. But actually you can apply it to the motion of any element of a string. So if I'm looking at any little, for example, this dark element of that particular string, the fact that the string is pulling from both ends means that if it's bent, it will try to stretch itself out. And that stretching itself out will overstretch it so it bends to the other side, and it will vibrate up and down. And we can solve these equations. And this is the equations for the moving string. It's a little bit complicated because the string, of course, moves all the way along the string, but the physicists, we can write down that equation, we can solve that equation from Newton's laws. And that leads to harmonic vibrations. Okay, so that leads to the frequencies of oscillation of the string on the violin. So while Pythagoras thought that numbers rule the world because the gods like integer numbers, Newton actually tells us there are physical laws that rule the motion of any object. And these equations following from the physical laws, they lead to these things. And they lead to the special frequencies. So if I have this wavy motion of a string, the fact that it's attached in both ends means that it can vibrate at one frequency. And the overtones that I'll come to in a second. So we love that stuff, of course. Here's, not only is it, it's a string that moves, but it's actually the whole body that helps transmit the sound. So when you're playing the violin or guitar, the string defines what frequency, but then the whole surface of the instrument is, of course, vibrating. And it's kind of fun, because if you play a high-pitched or low-pitched sound, you actually get different motions. It's a bit like a bass speaker and the high-frequency interval speakers and loudspeakers at home. And any instruments, of course, here it's the membrane that's oscillating, in the organ pipes, it's the sound that stands in the organ pipe. And we have equations for that. Okay? These are classical equations that describe how the air pressure waves are propagating inside these pipes. So this is classical physics. And here I show you the violin again with just the fundamental tone of a string, but in fact it can also move in this figure 8. And you know that because if you take a skipping rope, there's a certain frequency at which it will go up and down with large amplitude. And then if you double the motion, then it makes this figure 8 in front of you. If you triple the motion, then it makes a figure like the one I'm showing you here. So this is something we know from the schoolyard, from when we were kids. And the frequencies at which this occurs is the basic frequency, 2 times that, 3 times that, 4 times that, 5 times that. So these are the natural overtones of the string, and actually all the string instruments. If you take the clarinet, I just have to show you because I have a clarinet myself, it's a little bit different because it's closed in one end and open in the other one. So it doesn't have the same condition on both ends. It's actually minimum, always 0 here at one end, but maximum oscillation at the other end. That means that the overtones are going to look like this and like this. And if you look at what that is a consequence for frequencies, it's actually that the overtones is not the octave 2 times, but 3 times and 5 times and 7 times. So that's why when you play the clarinet and you just play harder or you push not the octave button, you don't get the octave, but you get the 5th inside the next octave. So that's a physics. I don't want to be boring and make physics instrument boring physics to you, but I find it deeply fascinating that very simple mathematics is also explaining why these beautiful instruments sound as nice as they do. And the saxophone, I also have a saxophone, it actually plays these overtones, although it's also closed in one end and open in the other one. And I love to ask my physicists friends, why is that? Why do you have that difference between the clarinet and saxophone? This is a super nerdy quantum question, actually, because any quantum physicist, after 2 minutes of thought, will know why the saxophone does play the octave. But not a classical physicist, but a quantum physicist will. Anyway, So in my talk, and this is not the introduction to this talk, but in the talk that I generally give when I talk to Kim, of course without slides, but I'm just sitting talking, I like to tell this little story, say let's warm up. I don't want you to just know some fancy words about quantum. I don't want to say they're qubits, they are both 0 and 1 at the same time, let's compose on that. I say you have to spend a few hours with me, where I drag you through all of physics in such a way that you also know where does this come from. That these are not just postulates and weirdness, they are actually real theory, we understand what it means, we have equations. It sounds odd with quantum mechanics, it sounds as if the physicists are just guessing about things. We know things very precisely in quantum mechanics. There's nothing we know more precisely than quantum mechanics. We can make predictions in quantum theory where numbers we say are being measured with 12 digits precision. I mean, it's the same as not knowing how many people are exactly in this world. It's actually, if you stack us all together, you know how long we would be with centimeter precision. It's just crazy. So anyway, I'll tell this story, you already saw it, and then I jump into the quantum world. Because there's a really, really strange thing observed in the 19th century, and that is all pure matter, atoms, hydrogen atoms, neon atoms, argon atoms, they all shine light when you warm them up, but they don't shine light with all frequencies. They shine light with very special frequencies. And frequencies, when you talk light, is the same as color. So when you shine light through a prism, then you know that you see all the colors of the rainbow spread out in different directions. That's actually also what happens in the sky when you see a rainbow. That's water drops who scatter this light. And when you take the sunlight, you see all colors. But if you take the light from a lamp, which is containing, for example, a gas of hydrogen, you see only these colors. And when you take neon, you see red colors and other colors, but only very distinct colors. And nobody knew until 1913 why that was the case. But we knew very well that it was the case. And this is the reason we have quantum mechanics. But it's also the reason that it's so closely related to music, because these guys also have only very particular frequencies. The guitar doesn't play a continuum of tones when you pitch a string. It plays the basic tone and the overtones, which corresponds to a few frequencies, like a few colors of light. So there's deep analogies between the mechanism, the mathematics of music instruments, and what leads to this phenomenon. So in that way, quantum can go one way to the music, but music certainly also goes into the quantum. And there's this concept, synesthesia, where you confuse things, you see colors associated with every letter, you associate any number with a fruit, or you do all these crazy things that the mind can do. And I like to think that there could be a similar high-level synesthesia between physics concepts and music concepts. But instead of trying to defend that for you, I just want to show you here this idea of splitting colors into the rainbow. If you take that with the sun spectrum, you see all colors. It's cut up in pieces here, so otherwise it would be very long. You also see some stripes, and these dark stripes, they are the special lines I was talking about. It turns out that in the solar atmosphere, there are the same kind of atoms as we see on Earth. So these orange stripes that they see in the spectrum from the sun are the same as the orange light you see when you ride your car on the highway from the lamps. Because in these lamps there's a gas called sodium atoms, and they are exactly the same frequency. So we know that this is actually sodium atoms in the atmosphere of the sun. And there are 10,000 lines in this spectrum, and all of them have been identified with the individual atomic types we also have on Earth. So astronomers are super happy about this fact, because it means every time they see a star or a galaxy anywhere, they can just make this spectrum. And when they make this spectrum, they can tell exactly which atoms form that star, even though it's super, super far. Helium is named after Helios, which is the sun, because helium was actually observed in the sun spectrum before it was observed on Earth. 10 years before any chemist had ever seen helium as an atom, it had already been seen in the spectra of the solar light. So this is a fantastic thing. At that time, they maybe thought we would never see it on Earth. It's a particular stuff that sits in the sun. Anyway, here's a nice exploding galaxies, a dust cloud somewhere, and I can promise you that my astronomer colleagues have taken every single dot in this picture and done this spectrum analysis to find out which atoms are where and how they behave. So it's super exciting. Now, why do atoms have these specific colors? Well, it's an interesting story. This is what Niels Bohr got the Nobel Prize for. He made this model of the atom in 1930. He said an atom consists of an atomic nucleus and an electron or more which are orbiting around that. Then that doesn't give particular frequencies, because you could orbit at any frequency around that central one. We're back a little bit to Pythagoras' planets around the sun, and there's no special distances in classical mechanics for such an electron. There's no special speed. But Bohr, he just made what he called postulates, that you can only be at that distance, or other distances, but very special ones. And when you're orbiting around here, then you get then also certain characteristic frequencies of the light emitted when you jump from this one atom to another atom. So you have an energy of the light, which is associated with the energy of the electron in the atom, and that light being emitted corresponds to the particular color sequence. So this is 1913. Bohr got the Nobel Prize in 1922, so we have actually been partying for the last year in Denmark, celebrating that Nobel Prize to Bohr. But it's a nice theory, but it was only a postulate. It's not a theory. It's just a smart guy who says it could be like that, and that's not how we do physics. I mean, I can promise you physics is a little bit more solid than just doing things like that. And a French physicist, he said, I want to derive these orbits. Maybe what makes this particular circumference or diameter magical is that there could be some kind of wavy phenomenon, and this wave should bite its own tail. Because only if it bites its own tail will it be allowed. And then you could imagine now it will not be any distance would be allowed. You could add one or more of these little oscillations and go from one to the next orbit. It's a crazy postulate. It's still not very good theory, but at least it's creating some ideas. You'll also see the connection now to the string in the music instrument, who play special tones because they have to make the patterns that fit to the length of the instrument. Now the atomic system, as proposed by Belgrade, has special frequencies because it has to fit to the length of these particular orbits. Now, okay, so here's the picture with the instrument doing the same thing. This is how a wave equation looks like. And this is Erwin Schrödinger, who, I think I moved my mouse a bit away from his nose. There you go. It's still there. Okay, whose mouse? Is it this mouse? Yes, it was the
3 little mice.
There's a famous story with Schrödinger's cat, so we cannot have a mouse. So this kind of equation is an easy equation in physics. If somebody says wave, we have sound waves, we have electromagnetic waves, we have many different waves. Such waves always obey an equation that looks like that. If you're not familiar with math, you think it's a hard equation. This is an easy equation. This is Schrödinger's second attempt when he was trying to write down a traditional classical wave equation, but treating now maybe this motion in the atom as a wave thing. And when he wrote down that equation and solved it, he got funny solutions, wave patterns. So here's water waves, and you know if you throw a stone in a pond, it makes nice wing patterns moving away from that stone. And when you solve this wave equation, you also see such wing patterns here, for example. But you see many other patterns. And these patterns also had the same frequencies as Bohr's postulated model. But now there's an equation, now there's a theory. And that equation is what we call quantum mechanics. And this equation we have been solving since Schrödinger wrote it down in 1926. It always works. So physicists, we are not thinking that we know everything, but we are happy when we have an effective theory that describes everything we can observe. Okay? Every time we observe something that disagrees with our theories, that's good, because then we can have a way to discover something new. So this is the right equation for now, and probably also for a long time into the future, because it's hard to imagine experiments that will violate this Schrödinger equation. So it describes atoms, molecules, why iron and copper conducts electricity and heat the way they do, and so many other things about daily life. The pictures I show you there are not so different from the guitar picture. Here you see two areas at low frequencies, here you see two areas bouncing in and out in Schrödinger's wave function at low frequencies. And here you see these 6 areas, and here you see 6 areas in the Schrödinger wave function. And that's because the wave equation is a generic type of physical theory. But now we know that the microscopic world is doing wave theory. And in fact, I write here that the atoms are tiny music instruments. You can see they are much closer to music instruments because they are quantum mechanical than they were when they were classical, and having an idea that some particles are moving around. The fact that they do this wave stuff is very similar to the wave stuff that's done by your music instruments. So this is a fascinating story. The wave function is in itself is exciting. So now we have this little music instrument, but what is it actually that waves? And of course, you're music people, so I'm sure you know, maybe some of you hate Greece or some of you love Greece. It's actually great And it has nothing to do with John Travolta, but Olivia Newton-John's grandfather was a German scientist called Max Born, and he was the one who interpreted that this wave function is what it actually means. So it is a really crazy theory, quantum mechanics. It is not such that the electron is a wave. It is such that our theoretical description of that phenomenon is by a wave theory. It is a description of a microscopic world where we can actually not really see what's going on, but there are phenomena we need to describe theoretically. It's as Ivana was quoting Niels Bohr, that everything that's real is made of something that's not real. It's not even that it's waves, because a wave is also real. Bohr would rather say the electron is a particle nor a wave. It's a description, that's the wave description. And that allows us to make some predictions for experiments. And what Born told us was that the prediction is, if you do a measurement, you will see the particle somewhere as a particle, but with a probability which is given by that pattern. So the places where it's very white, you will often see it. The places where it's darker in this picture, you will less often see it. And this is confirmed over and over again in physics, right? So this is what we know, that we have this funny probability theory. We don't have a real particle being a wave, not necessarily at least, but we have a prediction for many different things. So we can predict energies with high precision, and we can predict what an experiment will look like. I can never predict precisely where I see the particle, but I can tell you that it will be half of the time to the right and half of the time to the left in this picture, or it will be with a high probability in the middle of these white dots rather than on the outside. But the actual place in every single experiment is always random, fundamentally random. Now, and since I'm not going to talk about quantum computers in this talk, I just want you to know that when we talk about quantum computers, the ability to formally, not having decided whether you are left or right, means that this particle here has some kind of potential ability to be both left and right at the same time. And that's the number 0 and 1 potential in a computer. So this is a particle that if we can make that work inside our computer, it can treat bit values which are 0 and 1 at the same time until we measure, and then they randomly collapse and become 0 or 1. So there's much more. Actually, there are whole courses of quantum computing that I cannot give here in the middle of this little talk. But now I move into this quantum discussions that we had with Dave. Oh, sorry, Vlatko. So Vlatko Vedla was also mentioned earlier. But this was a Danish character. so with all my wonderful colleagues here, and we really, as Ivana also referred to, we really try to avoid merely illustrating physics phenomena. But of course, we are discussing the physics phenomena. If they're interesting enough, they can be the inspirational material. So that's really how it works. So here's Kim again. And with Kim, we played with the atomic frequencies. So now you know more precisely what are these atomic frequencies. Atoms emit light at very certain frequencies because of a particular wave nature. And you could either think about designing an instrument, the state where the atom already is an instrument, but designing an acoustic instrument who has the same kind of frequency patterns as you find in the atoms. We cannot hear optical frequencies. They are 1,000 billion times faster than sound frequencies. We have to scale them down, but I could maybe build a cowbell who sounds with the same overtone spectrum as the hydrogen atom spectrum of frequencies. We also had recorded image and sound both from my university, and I understand now we have further enhanced the database of sound and patterns. And then there are various techniques and concepts in quantum physics, something called Feynman paths. I'll show you in a second, Feynman diagrams, what they are about, and how Kim and I were discussing those for some ballet projects. But again, now you see there are certain frequencies in the atoms. If we say as a creative, it's actually not even creative material. It's actually taking everything away from Kim except a minimum of things that are at his disposal, namely those frequencies. And then he can compose with only those frequencies. And then he walks around for a week and listens to that particular scale, and then the music comes out. But it's a super exciting thing to attain. So there's a nice formula in the case of hydrogen atom, who says what are all the frequencies. It's what I call an analytical formula. It means that I don't need a computer to tell you what the frequencies are. I just have to put here in the place of this number n and m any integer, 1, 2, 3, 4, 5, 6, 7. And then when I to make that subtraction in two terms, I get a number which gives me a frequency of light. And if I take the series ending up with this n being 2, then I get 1/4, minors. If M is 3, 1 over 9, 1 over 16, 1 over 25. And those numbers here, they look like these numbers I've written here. And these numbers could be directly interpreted as sound frequencies in hertz, and then we can play them. And that's what we did with Kim. And we took other series. So here, we just plugged them into a piano. so these frequencies, they could be sitting here. So this is y-axis here is actually these numbers. So this is the frequency I want, and these blue bars show by their height what is the frequency of that key on the keyboard instrument. Okay. So you can see that, wow, there's a lot of key we are not allowed to play if I can only play the ones. And there also seems to be a terrible clustering, but that's how atoms work, unfortunately. So there was not much fun for Kim to do with this series here. But then we can also take another one, but put this number 6 here. And then I get some other numbers, and then, okay, at least we get a larger separation, we get a little bit more keys for the music instrument. And you can see the consonants, of course, went away now. We're going to play this on the piano. We're going to write it out as normal sheet music, but it came from that place, and that was the inspiration to then later make the music. So here is then this translation and allowance. Of course, there was a number of choices, also aesthetic choices from our side. Which number should I precisely put here? I cannot put the optical frequencies, so I have to scale them down, and then you can transpose as much as you like up and down. We have already transposed by a factor 1,000 billion, and now we can always take another factor 2, that's an octave, but of course we can do many things. And we did all of that to find something that fitted also to the instrument. And I want you to know that in the late 19th century, understanding atomic spectra, people had made this kind of diagrams, which were very similar to some of Kim's diagrams also. So these are actually levels in calcium ions who have certain transitions, and the numbers are written here. These are actually the wavelengths, but that's equivalent to the frequencies that you hear when you play these different combinations of tones. This N and M business over here, that's the different lines. I can draw lines between when I do the sounds in this picture. So it was an almost scientific approach, rediscovering what chemists were doing in the 19th century to form the music. And LBU made a fantastic thing, and I will be forever grateful for having been part of that and also being a part of the performances of this fantastic music that Kim wrote. So really great. Then Kim also wrote something we call VEC music, so that's not part of the quantum music project, but I think I'm allowed to tell you about it. Anyway, Bohr's theory was also not part of the quantum music project, then you got that too. So there's something called quantum gases that were first made in the 1990s. This was suggested by Einstein and Bose back in 1924. And very exotic phenomenon. And Kim had heard about it, and could we learn something from that? And I'll not tell you to do the physics, but let's say yes, we could. And this is the Aarhus Sinfonietta with a solo cello player. This is me speaking, so I just want to tell you that was part of it. They said, do you want a PowerPoint? I said, no, I don't want a PowerPoint. I want to give my talk on orchestra. So in fact, we had the opportunity to ask some of the musicians to illustrate parts of the little presentation I gave before that. So there were different compensates, wood and flute compensates, brass compensates appearing, and the solo cello was like the free party flying around and being sometimes trapped by the other atoms. It was also a super nice experience, a wonderful concert. So yes, you see, the musicians had great fun. That's nice. The audience also had great fun. Particularly like this picture because this is my daughter. So that was fun. Great project, and working also with the musicians because I took part in some of the rehearsals and discussing with them because they said, "What is it really you want? What is it you want?" I said, "Well, I don't want something. I'm just bringing knowledge about the physics. But if you ask me, what is it actually that's going on in the physical world, I can give you an executive summary of the physics too, and I think that has been fantastic. Now with the ballet project, that was also interesting because when we do physics, sometimes we do equations, but the equations are always representing processes, and sometimes it's nicer to just draw the process. Physicists can immediately understand the drawing, and then we can translate it into the mathematics and do the mathematics afterwards. So this is actually drawings invented by a physicist called Feynman, where he just draws which particles are coming in, what is happening. This is the famous W particle that gave a number of Nobel Prizes, explaining the decay of microscopic particles. And these kind of drawings are the kind of things that is not quantum mechanics yet, because these guys are not particles, they are actually waves, and they're all over the place, but we know that we have to move this picture around and distort it and put all of that together in a big complicated sum, but we make this drawing. And it's nice because, it almost looks like choreography. I mean, this is a kind of tango, a kind of odd tango perhaps. So when talking to when Kim introduced me to his ballet colleagues, he's also at the Royal Theatre where they had a school of ballet, then we figured it would actually be more fun to explain to them what is quantum physics by using this kind of stuff than using waves. So we talked to them about these diagrams. And this is diagrams I was drawing to Kim. This is a very simple one. This is just one particle moving. And then, of course, we said we could imagine that this is sheet music paper. So this is Kim who took my drawing and put it onto the sheet music paper. And then you can imagine, of course, if this is time going this way as in music and with rotation, and then instead of space, this could just be some kind of tone. Of course, this is again my drawing, and when I said you can think of it like that, then of course you won't do that. He didn't do that. You never heard this crazy thing being played. Of course, he did more fun things, and he wrote a super nice article about that actually that you can read. Here are other diagrams where you have two particles moving along, and then in between them a particle and an antiparticle are created and disappear again, and that actually causes important physical processes. But you can also see, putting this into this sheet music, it could actually be two tunes being played together and a little mini tune appearing and disappearing again. That's how I explained the phenomenon to Kim, and this is of course not what he did. Okay? So never, people never do what I tell them, because I explicitly instruct them, never do what I tell you. Here's a thing that Feynman discovered. You could also imagine a particle moving forward in time, and then it moves backwards in time, and then it moves forwards in time again. Now, a particle moving backwards in time is the same as the antiparticle moving forward. So this is a real physical process, but we can also interpret it in a different way. In the physical world, it's a very important process in the physical world. For a musician, it looks pretty easy, right? And of course, you can have different tunes being played at the same time. And I said to Kim, maybe the particle is minor, maybe this is a major piece, or maybe it's like Bach who writes forward and backward the same piece of music. And of course, he never did that. but there was no doubt that he understood exactly what we were talking about. He did something else which was fun. He said, this is a really cool idea. In these diagrams can in physics completely retain their physical meaning no matter how I rotate them. I can roll time into space into time. And then of course their story is a different one because you read it now in a different way. You see I can actually rotate this one so that this one is not going downwards or upwards, but going backwards in time or backwards in space. And these rotations, called big rotations in technical terms, really fascinated Kim. So he took some music, I think it was by Vivaldi, and then he cut it up into pieces and rotated it, glued them back together again, so that the different segments in time were now appearing in a different order. And of course, he never composed anything like that, but he said it's a pretty funny idea. And of course, it is a pretty funny idea. It gave several Nobel Prizes in physics. So, and it was fun to discuss that with the choreographers too. So this is Calidora Fontana, who's a choreographer and dancer at the Royal Ballet in Copenhagen. Tim is also a choreographer and dancer at the Royal Ballet. And we had two separate projects with them. I don't want to distinguish them for you here. But then she created a ballet and Kim made the music, and we had me standing on stage and talking to people and doing a little bit of motion just to indicate how I would do it and how, of course, they did it better. And then we had the ballet, which was fun, and we had the question session that I mentioned before. It was in a tent at a kind of open fair event, and they had to break down the back wall of the tent because there were so many people who wanted to see it and stay for the questions. It was a massive success for the theatre talk. So and really, really great fun. Okay, so now maybe just a last thing, or on the physics side, one more recent thing. So as Ivana said, I visited Delft where we had wonderful discussions with our music friends, and we were talking about what can we do with the music instruments. So I already showed you how taking the colors of light and putting them into the piano, then it's such a waste of good piano that you're only allowed to play such a few tones. In fact, I know you play quite a lot of tones when you play quantum music. But anyway, we could maybe also do other things inspired by physics. So talking with Angela, we just took this thing, now the boring physics that all of you probably know, maybe in different terms, is that all these keys correspond to different frequencies. That's the height of these blue bars again. And you could, maybe if you have a pitch standard of 440 hertz, that's the A stage here. What is actually happening is that for every half tone you go up, you increase the frequency by 5.9463%. Okay? Then if you go up 12 half tones, you have exactly multiplied by a factor of 2, and that's the octave. And if you go up to the fifth in the next interval, here, put it right at all, or here's put down further down here, that's also an interesting interval. It's in fact, if I take this doubling here, this is the octave, and the tripling, you are super close to the fifth. So that the octave is a good one. The upper G, usually the formula I just told you before, is not exactly 3 times the frequency, it's a 2.996. But that's close enough that we don't really notice the difference. So these natural string overtones, they're actually equivalent. If you play this deep C on the piano, the same string plays this C, and the same string plays this G. And it also plays these tones, of which some are not even tones on the piano. So I just put the arrow in crazy because they don't really fit the tuning of these keys. And the reason we think these intervals, amateur musicians like me, think these intervals are nice, is not because there's anything particular about an octave or a fifth. It's because when I play this key and I then play this key, I'm playing a tone which is already there. We love familiar things, right? So when you already hear that and you put that one, it sounds good. If I play any other key, there's maybe a dissonance, but there's not a dissonance when you play that one because you play it the exact same tone which is already being played by the other string. And that is why the chords sound good. And that is actually something we were thinking about. If we want to make new scales, you have to be careful. If I just put random frequencies, then the chords will not sound good anymore because you won't have this phenomenon occurring. So do we have any freedom to play with the keyboard? So this is what we discussed when I was in Delft. And we really want to see, can we compress or inflate the scale? And so I told you, you multiply the frequency by 2 or by 3 when you play these keys. What if I wanted to compress the piano such that the frequencies would be closer? So the gap from this C to this C would not be a doubling the frequency, but a much shorter interval. Okay. Of course, you can just say that you shouldn't increase by 5.6% every time, but only increase by 4% or 3%. Then the tones would come much closer. Maybe this C would sound like the A on the other piano, or the G on the normal piano. So I want 1.55 for the octave, I want a factor 2 on this fifth, although they are normally actually a factor 2 and 3. But also pull the piano out so that the octave is suddenly a larger frequency jump, so it sounds like the fifth on this piano, and then this fifth here is going to sound like the next octave on the other piano. And if these were electronic instruments that were just playing one frequency, we're actually free to do that immediately. But if you do it on a piano where you just pull the strings and tune it for that, then you will miss the overtone. This guy will not sound good together with that one anymore, because the overtone of that string is not the same as that tone. So if you want to do this kind of design, you have to change the frequencies, but you also have to change the physics of the string so that its overtones are not the doubling and the tripling as they are in normal strings. And this is something we discussed how we could do that. So we like the octaves and the fifth for the reason I just said, because they are already present as the natural overtones. And they sound together at the same frequencies. But if you want to have this compressed piano, then you can only make it sound right if you actually make the overtone spectrum of the tones right. So of course, I could have given this as a crazy classical suggestion, but we are inspired by this magic eigenfrequencies appearing in wave vibrations, and we could also think about a quantum instrument proposing which could be the new fun intervals to play with, inspired by this particular atom, this particular one. I can give you a little, if you want to do something relevant to the climate agenda, then we can provide frequencies for CO2. Wouldn't that be nice? Well, it could be nice if you feel for it and you say that's something. Here's the CO2 symphony, and now we have musicians and physicists standing together for making a better climate. Well, okay, this will be a little cheesy, but the way we have to restrict ourselves when we want to bring things from physics and physical sciences to art. We have a too big catalog. Sometimes I was asked also by Kim, do you have other frequencies? I said, yes, I have too many other frequencies for you. So we have to find a principle. We have to find what is the idea that makes us select those frequencies. Okay. Now, a final thing which we have not done yet, but we have talked so much about it, and I think I see glimpses of it, of course, in the work from Delft, But of course, now you talk to experimentalists and you integrate some of their experiences. So I can just briefly say that, of course, the wave particles nowhere and everywhere at the same time. It is this superposition thing. This is something that Keith has actually been playing with quite a lot. It's something you can actually do with music, which is completely common to all music, is to have several tones being played together in harmonies. And this thing that you actually can have two tunes being played at the same time and we can feel it and hear it, that's maybe the closest we come to this quantum idea that particles are different places at the same time, in so-called superposition. The particle is never really addressed, that's a vacuum, and the vacuum we heard about, the composition, it's never completely dark, you cannot turn off quantum light, and if you amplify it, you will always hear it, and that's also been used already. Empty space is not really empty, it's an inferno of particles and antiparticles that are coming and going all the time, and that's a thing that can be played, of course. And then we have the really weird things about things being correlated all long distances, something called entanglement, which we try to put into the ballet, at least I try to put it into the mind of the choreographer, and then whether it actually made it to the ballet is hard to say, but there were two dancers, and it looked pretty spooky what they were doing, so I think it could actually be the spooky action at a distance that happens in the tango. So, and it's all about, is this an engine that creates something which is good, that gives us a new experience out of the music or whatever art we're working with. Now I want to come back just on the last slide or two on what this brings back to me, except for giving me new good friends and giving me creative things to think about. And I'd like to start out showing you a few quotes from some Nobel laureates. So every year when they give out the Nobel Prize, they also have a discussion, a roundtable discussion with the Nobel laureates, and then they are asking them about different things. And I remember when I was a child and we had only one TV channel, it only showed TV 2 hours every day, then we always see this. It will always be boring TV, not child-friendly. But this I thought was actually pretty interesting. So there was an old man asking other old men if they believed in scientific intuition. Today, fortunately, there are also a few women around that table. But at least, do you believe in scientific intuition? What does it mean to you? And they all had an idea. There's never a scientist who got the idea out of hard work based on what other people had been doing before them. There's always this glimpse of intuition, inspiration, and it never comes by hard work. It always comes by something else. And there was a whole book that came out of these interviews, and I just took a few quotes for you here. So this is a medicine laureate from 1986. You've been thinking about something without willing to for a long time. Then all of a sudden the problem is open to you in a flash, and you suddenly see the answer. It typically happens to me that I'm thinking about something and I just cannot make it work at my desk, but then it happens on my bike or when I'm brushing my teeth. Actually, brushing my teeth is always a good idea. So that's why I never have holes in my teeth, because I go to my toothbrush when I have a problem with physics. Here's another medical doctor. If you try to permute your knowledge, nothing comes out of it. You must give a sort of mysterious pressure and then rest, and suddenly, bing, the solution comes. It's really, really interesting. And here's something I really loved when I read that on chemistry. There's another aspect that I would add to it, and that is, I think, taste. Taste in almost the artistic sense. Certain individuals see art in some undefinable way, can put together something which has a certain style or a certain class to it, a certain rightness to it. Actually, all physical theories, everything I ever did, the solution that was the right one in the end was also the prettiest one. Not only because you fall in love with your own solution gradually, but that is an aesthetic to the right theories in natural sciences. And the way we find them is not by that we look for the one who looks the nicest, but that's because we are guided there by this kind of intuition. So I really think and hope that as scientists we should actually develop a little bit more our ability to get this Bing experience. And that Bing experience is not by working harder in the lab, that's actually by working harder on a general mental openness and whatnot. So there is a lot of hard desk or lab labor in science, but I'm sure there also is in art. But the real innovation, the real breakthrough, is not what happens there. It's this funny cognitive process, this rightness that this gentleman was talking about, or mysterious pressure that we heard this lady from medicine. So how do we use the full capacity of our intelligence to actually make this kind of progress? And this is something where I actually think I can learn from the art, interaction with the artist. So why? well, I mean, artists have always been reflecting on our lives and our experience and communicating them, putting them in new context, and forcing us also to see this is okay, I have to look an extra time on Kandinsky's music or concert picture here, but then of course I can see the grand piano, and I'm sure the yellow stuff is the music. So sure, but that's waking your mind to this kind of experience. So and that's maybe this synesthesia thing that I talked about before. There was a lady attending my lectures. She's not making this kind of paintings, but she actually wanted to put Schrödinger's equation into paintings. But she didn't want to just put the Schrödinger equation into paintings, as I did here with PowerPoint. She said, I need to learn what it is first. So she actually attended a 12-hour course that I gave on quantum mechanics. And then after that, she felt now she had some right to put Schrödinger's equation into her paintings. And I think that was a cool idea. I mean, at least now she knew what the equation was about. So I think it's, let's communicate a bit more. And also I want to tell you, just to make sure that you also get that message, that the science we produce out of the natural science environment is of course made by people. So I mean, we are not robots, and we are not like the robots we heard speak before reading poetry at the concerts. We are looking at a science frontier which is so huge and so fractal that the most important processes we do is actually the decision process of what we want to do. And that decision process is not mechanically given by our combined knowledge, but it's given by this inspiration, all these things. And it's very, very human. It's also very, very interesting to see how different we are and how some people like to really go in the direction I find boring, and I go in the direction they find ridiculous or boring. But that's how it is, right? And that's why we have to get stimulated by what makes these choices the more interesting ones. So this is my last slide, if anybody should worry. Here's a picture of Niels Bohr, and this is one of the famous atomic model pictures. I like to this particular quote for this occasion. Bohr realized that quantum mechanics is an odd theory. It's not a theory about what the world is, it's a theory about our knowledge about the world, because we are not saying particles are waves. We are not saying that particles literally are several places at the same time. We are saying that our description is like that. And for that reason, he was very often comparing the description of quantum physics with other ways of describing phenomena in the natural world, also in our daily life world. Here he says that we must realize that when atoms are concerned, language can only be used in the same way as within poetry. Also, the poet is less bothered about describing facts than about creating images and establishing mental connections. I think this is what this project has done to a really large extent. We just replace, or at least add to the poetry, the music and the ballet and the painting. With this, thank you for your attention.
Just jump quickly for a Q&A session. Thank you so much, Klaus. This was so fascinating, and just to try to grasp this world where we live. But I was absolutely fascinated with what you said in the end. So it is actually this kind of epistemological dimension of quantum physics, and also semiotic dimension. It's all related not to how the world is, trying to answer those ontological questions, but actually how we comprehend them and how we put them into words or into music or into theories, equations, whatever. So how we translate that into something that we can perceive and comprehend. So I guess that's...
I couldn't have expressed it better. I mean, the Bohr's interpretation of quantum mechanics is that it's an epistemic or epistemological theory. It's not an ontological theory.
Yes.
And for him, he doesn't say that the real world could not exist. He just says, I don't see any use for it. Because my description of what I know is what I confront with what I measure. The other thing is pure metaphysics, and actually for Bohr, non-necessary metaphysics. Doesn't mean that all physicists that we need. And there are other schools in quantum physics. Einstein and Schrödinger himself, who I showed in the beginning, they strongly disliked this epistemological thing. But they lost all their debates with Bohr.
Yes. I mean, did they prove their point? Not really. So.
Not really. But there are other younger scientists who have similar points, and that's exciting. That doesn't have to be one truth about what is quantum mechanics. Maybe there can be other quantum music projects that are more ontological than they.
Okay. You know, just an observation before we start with the questions. one of the guys in this collection, Andrew Gardner, whom I've mentioned, his father is actually a priest. So he grew up in this really kind of religious family, and he became a quantum physicist. And so we always ask him, so Andrew, do you believe in God? And he's like, I don't know, I'm searching for answers. So he's basically trying to resolve this sort of ontological kind of mission in his head, trying to see if there is evidence for one way or the other. But he has been working on it, and actually it's not about evidence, it's just about how we interpret things that we see. And that's what the artists are doing as well, as we have hopefully shown. There's such a huge range of possibilities how we can use this quantum world to inspire artistic creation, not just in music. You have also seen these artists from different disciplines and how they have explained what they're doing in the catalog for that exhibition. So it's really a huge range and how we can learn from one another. So I do hope that all of you who have not read this collection yet will find some time to do it. Just because of these fascinating articles by Klaus and Kim, who explain some of the things that he has shown here. There is also an analysis of Kim's composition by me and my other quantum particle, my twin sister. So the two of us were born as identical twins, so we grasped this phenomenon of being in two places at the same time, constantly swap places, with one another. So it's not hard for us to comprehend that on a conceptual and real level. But yes, we also analyzed this Kim's composition, superposition, and we tried to prove that also Pierre Boulez would be very happy with quantum music, because actually it was him in the 1950s who explained this desire to create new technologies, to actually not rely on traditional instruments all the time, specifically because, as you said, they're so limiting. And let's see if we can pull away more sounds. That's how we got the prepared piano and all these different instruments. That's what we are doing now with this gizmo that we put on the pianos to create new colors, new interpretational possibilities. But I think that there was one important difference. So all these big modernists like Boulez, Stockhausen, so on and so forth, they all thought that they found the right way to write music. They were very absolutist. They had lots of money, they had lots of infrastructural support that we no longer have, and we had to apply for EU projects. They had the CIA to finance their research, but they were always like, this is the right way to pursue new music. This is how everybody should be writing. And they created lots of epigons. And by doing the same boring things all over again, that's how we lost the audience for this modern music, because it was so dominated by these massive figures. Then in the end, people just switched off and went to do something else. So I think this puts forward a strong argument for diversity, for exploring all these different options and for seeing how actually we can pull this in as many directions as possible. Sorry for this digression, and now I'm very happy to ask the audience to ask questions.
I would just add, thank you so much for your talks, Steven and Klaus. It was amazing, and it was amazing also the process of talks and works all these years. And as you said, the music, the question of what is music is changed now, and it's not the same as in the modernist time. And we have such a great time in Delft and open so many questions. And one of the things that Klaus mentioned, this idea of compressed, what we call also inflation scale. I will just add that we work together with a very nice sound artist and technician, Ilya Georgievich, who is based in Berlin. And actually we moved from the piano and made kind of a virtual synthesizer that we used in the beginning of the concert, and that will be used more. So actually what Klaus said it would be very hard to do it on the acoustic piano, traditional one. But now with the digital technology, it's much easier, and this VST instrument will be also open source for other artists and generations of musicians. But I want to thank you again for that.
Any questions?
I think you will have a commercial market for that particular thing, because soon it will be Christmas, and then we will all be singing Christmas songs, and you will hear how your loved ones and yourselves often have a limited range or which you can sing. And that instrument will actually take any tune and you can play it the way it's written,
Exactly.
but now it will only span like half an octave if that's what you can do, or one full octave if that's what you can do, and it will still be the same tune roughly, and the harmonies will still be correct.
Like it could be like never more ashamed of being out of tune.
Exactly.
That is a commercial for
So I
that.
think we should think about a patent on that one, because that would be could be a huge market.
Any questions? Yes.
Hello, I'm composer.
Lavica, a young composer from Turkish music.
Also a researcher in music in Belgrade at University. And I have one question. Like contemporary composer, I don't see future of Boulez music, etc. I have to say something like that because we don't have, unfortunately, audience for that. But do you think that this quantum music have a future? What do you think about it?
I don't want to claim that everything quantum has a future. Today, when I'm washing my dishes, it's a quantum thing. It's written on it at least. But I think the combination, that's what we saw I mean, so it's more like the hybrid events. I mean, so it's not only, I mean, the composition, the event has to be honest. So if you make an event which is uniting science and art, then you do that in the process. You compose according to that if it's a music event. And then you can present it. And when you do present it, we have massive audiences. I mean, compared to what is normal. And I think that can have a long mileage. And of course, it doesn't have to be quantum forever in the future. Maybe we will fade out the quantum and then we will call it science music, or we will call that whole thing something else. So a new hybrid form. And this I actually believe quite a lot in that. And I don't know if I mean, of course there were famous musicians also historically who used other platforms. Glenn Gould started doing radio programs and is that, well, they were artists, so therefore they could also do that fantastically, right? But there should also be a preservation of the real music and the real thing of composition and music without having a story around it. So I don't think it should never be a replacement, but I think it could be an avenue. And the same thing when I'm talking about all these outreach, of course outreach is also not science. So it's actually also something I do make a distinction between my scientific talks, the science conferences, and when I'm doing this other thing. But they are equally important aspects. They're completely, they are both completely compatible with my life as a scientist to do both. Yes, yeah.
Well, the history of music changed. So if you had like the term contemporary music is more the same. And if you had a minimalism music in the end of '60s that opened the music to the larger audience, I think it's now the question for new generations and for you as a new artist to find a new ways how to present your art and how to show your art to the world, So.
And can I add something? This idea of quantum music, actually you can add to any musical genre, and that's why for sure it will last forever.
It's open to sing,
That open like the quantum physics is actually.
I think that's what I said about the Stockhausen and all these geniuses who actually were breaking new ground. And then it became
Stop
stable.
anyone else from
And I think that's maybe the highest risk for quantum music. That is that now we had fun and we were very creative, and now we do the same for 10 years. Yeah. And then it's better to stop it, right?
Exactly.
It's better to look and go find inspiration elsewhere. And we are still, so in Denmark we have a negative expression about all these academic people, we call them the eggheads. So it's also a little bit of an egghead project, because we are, and that's also what's so fascinating, right? I was talking nicely about working with professionals, And you're also not only professionals, you are theoretically skilled professionals, right? So we are actually researchers with a very similar background. I think it could be very interesting to find a way to engage the listeners more, and of course that's what my main motivation with the other outreach activities.
You always have to listen. You always have to think about the listeners, because the music is not about only the performing, but the listening process. So there is no music without listening, and that's sometimes we forget that. In everyday talk also, we don't listen to each other. We want to talk, just but yeah.
I had a colleague that was actually also in the Netherlands. He was doing a project with the pop musicians. And so that was very interesting. High Burman is in Amsterdam, and we talked about this, and he said, "Well, there was a big festival, and then they said, can you do something?" And then, so this is we can hold our noses about some of these more popular cultural things, but that was also a big event, and it was great fun, and I think he probably enjoyed that collaboration the same way as I have been enjoying our collaboration, because there was the work on something. Right? So I think that's also very interesting. But maybe it should be us doing that.
I think exactly. You should always find friends out of your circle, out of your profession. That's the way how you can, find something new.
Exactly. Now you have become my circle. I have to.
I was going to ask you precisely about this outreach that you spoke about in the beginning, and we experienced this sort of loss of audiences also as a consequence of the pandemic. Because now lots of people are simply used to sitting at home and turning on Zoom, and they don't actually bother to show up at an event. Even now that we no longer have to wear masks, and keep distance and whatever. I've seen that with festivals recently in Belgrade and in other places, empty seats, something that we didn't used to see before. Now that people know that everything is going to be recorded and available on Zoom and so on and so forth, they just don't bother. So I think that's why these extra outreach activities will be even more important now than they used to be before the pandemic. Because now we have to bring back even those audiences that we lost during the pandemic, and plus try to recruit some new people as well. So double the effort in a way.
You're right, and the massive events I talk about, the ones that goes to the movie theaters. I was a co-inventor of these events in 2005, so it's actually every year we did it. They became more and more popular, and from the beginning we made one dogma rule about it, that this will never be available online. This will never be something you can see on your own. Well, we make an exception. If you have a handicap and you cannot go out, of course you can get the link that the movie theaters get. But that should be the exception. This is a thing we do together, and this is a thing where it's the whole experience, and it works wonderfully. I go around, sometimes I listen to the people after the talk. We have and not everybody, but the ones at the university campus, they can actually go to the science museum afterwards and have a beer or a glass of wine, and then I'm listening to what people are talking about. And it's an institution. I mean, you can hear how there was a young woman saying to a friend on her phone, I didn't know what to do. I just wanted to crash with a bottle of wine and the TV, but it was only garden and cooking programs. And I couldn't relate to that. So I walked over for one of the science talks. So she doesn't even know what is the science talk, but she knows that there's always 10 science talks. And then she pops into my talk, and then she said, well, it was something really odd called quantum mechanics, but also kind of fun. And the reason she had fun, she was hanging out with this group of people that she met there. So I think bringing people back together, making events that make people come, and we had a huge turnout when COVID lifted. Of course now people needed this again, but we also had some who didn't come, but then they come the second time, the third time, because neighbors talk about it, and you have to come.
So that's so fascinating. I think lots of us here in the room had our mouths drop when we heard about this idea. And it's been going on for so many centuries now. And now an ontological question, because like in all these kind of polls in the world, the Danish people always end up being among the happiest ones in the world. Is this also because of this culture of sharing knowledge, learning all the time, not being locked in your own tiny little universe, interacting in a way, trying to improve, work on yourself?
There's one reason why Danes are often the happiest people in the world. I mean, many statistics show that there's one particular feature where we are actually different, and that is that we trust everybody we meet. I mean, you can call us naive, but it actually removes a lot of anxiety if you just instinctively trust everybody you meet.
Oh, I'm like that as well.
Yeah. Many people are like that. But so you ask Danes, would you trust anybody to look after your child if you have to go to the rescue in a train station? Sure, 99% of the Danes say yes, 65% of the Swedes say yes, 5% of the Italians say yes.
0% of the Serbs.
Maybe. So there's a general trust, which also means that you are actually always feeling happy when you're together with other people. I mean, you don't feel any anxiety in particular. Of course, you don't want to be a lonely young woman walking through a park in the middle of the night, because we're not better. Crime is not lower, and we are not more honest. And people also steal things and bikes and everything in Denmark. But we just pretend it doesn't happen because it rarely happens, right? I mean, so we are more realistic about what are risks, and that means that we are open with other people, and I think that's why people generally enjoy it. I don't think it's the learning so much, actually. I think it's more, and you know,
social.
We are Nordic people, so we are not sociable like if you go to Denmark, you find that we are pretty cold and distant people. We don't invite you to our house as a natural thing. But we don't mind sitting next to you on the train and having a chat for 2 hours, but then after that we say goodbye and leave you on your own. So it's the cultural differences. But I think this thing of going to these events, it's 100% nice and safe for everybody, and you are also open and you can have fun. Say, I don't understand what he's talking about. You can say that to a complete stranger and having a fun discussion about that. So that is something. Otherwise,
really impressed with that.
But then I also have to say one more thing, because when I talk to colleagues who try to copy this, when I say we do this outreach, and they say, we also have a Saturday, there's 500 people coming to universities in Germany, for example. Then I say, okay, did you also open the lab the next weekend? Because what we did was we actually just realized that if you do a single event like that, all over the world it's very popular. I'm sure the physics department here in Belgrade, if they made a public event, come and see the labs and hear a talk on astrophysics or whatever, there would be a lot of people coming. And then they would do that the third Saturday in January every year, and they would be happy that so many people come. And we just started doing it 6 times per day. and they kept coming, because there's actually really many people in these countries, right? I think this is not unique. This is just because you don't do it in other places, right? And then we try to do it carefully. I can tell you, when I make this talk, it was a crappy talk compared to the talks I give at a public lecture, because I make my talk in PowerPoint, then I give it to a guy who takes care of it, and then he has assistants making all the drawings beautiful. He says it goes on the big screen in a movie theater, it's dark, everything has to be perfect quality. The size of that file is many gigabytes. Big, and I cannot run it on a laptop because they put so much graphics into it. Not funky graphics, it's still my talk, but it's just all crispy and pretty. So we also try to make it a quality experience for
like a concert, with the visuals.
Like a concert, like you do, right? I mean, so you don't want to hear false in the music. You don't want to see false. But one thing which is also, if I just may say that, there's a lot of documentaries and TV and science, and they're very popular. People actually want to see that. But we can do something more. And I was at a talk by one of my colleagues, a biologist, who discovered actually electronic circuits in the sea bottom outside Aarhus, but it's everywhere. It's a way for electrons to go down and do chemistry. So it's actually not so surprising. It's just chemistry, but still quite interesting. There's wires in the sea bottom. And he was giving a talk about it, and then he had a glass of mud from the sea bottom, and then he looked into the glass of mud, and clearly eccentric professor, he forgot that there was 900 people in the room and 20,000 people on the live stream, because he saw something. And he was just quiet for a very, very long time. And I was in the back of the room, and I could see people leaning forward, and everybody went, quiet. And that will never work on TV, right? That works because people also have the feeling that this is a real scientist. It's not an entertainer. I'm also a physicist, and I give a little bit of myself. I tell, this is something that really fascinated me as a student, or this is something that I'm really curious about, not because it's useful, but just because I can't get it into my head. When you give a little bit of that to the audience, it's an authenticity that we also have. But you're also authentic when you have a live music performance, of course. You also feel that you're in the room with the musicians, right? So that's also very important. But I think you go ahead, do it, but just keep doing it.
Yeah.
And then people will come.
Yeah. Thank you so much again, Klaus.